So, we are going to start off a new module today. This is to do with database design and normal forms. Now, you have been studying various database schemas and posing queries on them and learning how to make use of schemas. But then you also have an exercise problem where you are designing a information system for some domain which you have chosen. So, in this context you would see that coming up with a design is very important. The design is the complete schema for the information system, and there will be certain choices there. When you are coming up with a design, you have to decide about what attributes should constitute one relation, should this attribute be in this relation or some other relation, right. So, there are various kinds of choices that come up there, and in this context we would come up with this question as to how do we know whether the schema that we have designed for the information system is good, and if we have some alternate schemes for the database, then which is better. Okay. So, these are the various kind of questions that will come to us when we are looking at alternate designs for information systems, the schema designs. Now, so in this module what we are going to look at is certain principles that have been developed in kind of evaluating these database designs. Okay. So, one of the important factors that kind of affect the design and also performance of the information system has been recognized as the issue of redundant storage of a piece of data. So, by this what we mean is, if there is some one piece of data, so it of course is belongs to certain attribute. So, if this attribute occurs in slightly different form in multiple relations in the design, then the corresponding value which is supposed to be same in all those places will also occur redundantly in 2-3 places, right. So, if a piece of data occurs redundantly unnecessarily in multiple places, then we call that as a data redundancy. So, this kind of data redundancy is seen to kind of affect our performance also, performance of the information system also. So, you actually might wonder actually how does that affect the performance, because the storage is nowadays not a big major issue. I mean, you have lots of storage and disks and external storages, secondary storages available abundantly. But the main issue here is that when you consider the ultimately the purpose for which the information system has been built, you see that it has to support transaction processing. It has to support everyday operations of the enterprise for which it has been designed. And in these transactions that these application programs that are invoked by end users, and they run thousands of times per day against this database, and they will be accessing the data. So, imagine a particular transaction trying to update a value for a particular update some value which is redundantly occurring in multiple places. So, if it is not updated in all those places where it is occurring, then it will lead to inconsistency in the database. So, we do not want that to happen. So, we will require the application to actually update it in all the places where it has been stored. Now, if you try to update it in some 2-3 different places in which it has been stored, all those will be in different files on the disk system, and then you will have to get access to them, and then so and then actually modify all of them. So, we will later on see how to access disk files and then carry out these operations. But at this stage it suffices to remember that this operation is a costly operation compared to memory operations, accessing disks file and then updating. So, if you have to do it at multiple places, it will add up to the time that the transaction takes in order to complete the task. Now, if the amount of time the transaction takes to complete the task is high, then the number of transactions that the whole system can handle per unit of time, which is called the throughput of the system, will obviously get affected. It will become lower. So, and if the throughput becomes lower, then the response time of the system in the presence of thousands of users for the system will also go down. So, all these are the various implications of having redundant data. So, how does redundancy occur, and in some simple kind of designs which contain just about say some 10, 15 schemas or something like that, some 20, 30 attributes, you may be able to figure out many things. But in practice, these database designs can tend to have huge number of relations and then involve some 100 to 200 attributes or something like that, in which case it kind of becomes difficult to kind of figure out what is happening in the scheme. So, are there any theoretical tools that we can make use of in studying these properties of these schemas and then make use of them in comparing our schemes, or if we already put in a particular design into operation and then we are now finding some kind of efficiency issues, can we kind of look back and analyze the design and then see where exactly problems arise. So, with all these goals in mind, a certain kind of theory called the dependency theory has been developed by researchers in 80s and 90s. So, in this module I will give you an introduction to this theory. We will tell you the fundamental principles that are there in this particular theory. So, these are the questions: how do we characterize the goodness of a scheme and how do we compare them. So, in this process what we will do is introduce what are called normal forms. So, normal forms are some kind of conditions that are laid down. So, and with a guarantee that if these conditions are satisfied by the scheme, the database design you have, then certain kind of problems do not occur. It is the guarantee that the normal forms give you. So, we will now go into the details. So, let us start with as usual, let us start with the example to kind of get some idea of what the things that we are talking about. So, I am going to contrast a correct scheme with an incorrect scheme and then see what are the kind of issues that come up here. So, let us say okay, these relations are not as necessarily the same as what you have seen earlier, but I am going to define them here. Student relation has student name, roll number, sex and student department, just for simplicity, and roll number is the key. And department relation has a department name, office phone and HOD. HOD is an employee. So, employee ID of the HOD will be there. Several students belong to a department and this student department gives the name of the student's department and is a foreign key referring to the department name, and department name is the key here in the department relation. So, this is a good design, it is a correct design. So, we have put student name, roll number, sex and student department here, and made it as a foreign key that refers to the department name and office phone and HOD. So what if somebody comes up with this following scheme, student department kind of. So I do not want too many relations to handle. So let me put all the information in one relation. So let me put all this in student name, roll number, sex, department name, office phone, HOD, put everything together. So you have some intuitive feeling as to this scheme is not that good actually. For some reason you may develop some intuitive feeling that this is not good. Let us see why, what are the actual problems that arise. First thing is there is redundant storage of data. Where is the redundant storage of data? Now, several students belong to a particular department, right. So, some 100 students belong to one department or 200 students belong to one department, and you can see that in this scheme the department information as name and what is the phone number of the department and who is the HOD of the department is kind of tagged along with all the students that belong to that particular department, because there is no other way, right. So if you say student name, roll number, sex and department name and office phone, so we have dropped off this student department which served as a foreign key and then referred to this, right. We dropped off that. So we directly want to give all the information about the student's department in the scheme itself. So now you can see that the office phone and HOD information and the department name information is stored redundantly. Department name of course was there earlier also in the scheme, but definitely office phone and HOD information is stored redundantly once along with each of the student that belongs to the department, and it is a wastage of the storage space. So now a program that kind of that is required to update the office phone of a department obviously has to change the value at all these places. If the 100 students belong to the department, in all those 100 tuples it has to change the place, and the main issue is this running time, because you have to change it at. Now the issue with running time is that transactions that are running on the database, we would expect them to finish fast so that the throughput will be high for the system. So if a lot of work is being done by transactions, then it will affect the throughput of the system. Okay, so not only this issue, there are a lot of other issues with that scheme. These are slightly different kind of problems, not necessarily with the redundancy, but look at here. This is what is called a insertion anomaly. There is no way of inserting information about some new department in this scheme, unless we also enter some details of some dummy student, because unless the student information exists in that scheme, the department information cannot exist, right. So you have to put some dummy student information and then put the new students new departments information. So you are kind of forced to introduce some details of some non-existing dummy student in order to introduce information about a department. All this because we have chosen to combine information about students and departments together into one scheme. You are able to see that, and you can imagine similar set of problems that arise there. This is called deletion anomaly. If for some reason all students of a certain department leave, then how do you handle the issue? You will be dropping the student rows. If the student leaves the institute for some reason, you will drop off that row. So if for some reason all the students in a particular department leave, and then when the last student leaves, then you are actually dropping off that row, and so information about the department itself is gone. So, that we did not actually plan for. So, we want to keep the department alive, hoping that some students will join the department at some point of time, right. So, we did not expect that, but it will happen in the scheme. So, if students leave, then at certain point of time the information about the entire department might get lost. This we have already seen, this is called update anomaly. Updating office phone of a department in value in several tuples has to be changed. And the issue here is that if for some reason you missed out one tuple, then or a few tuples to update this thing, then some tuples will say office phone is this, some other tuples will say office phone is this, and that is obviously a data inconsistency, and we do not want to have that in the database. Okay. So, these are the various problems that arise with bad schemes. Now, the question is how do we, in this case it was kind of obvious that saying that okay, you had two different logically different kind of entities, the student and the departments, and what you have done is to somehow forcibly put the details about both these things into one scheme, and then you got into trouble. Okay. But in a database that may have several hundred attributes, how do we kind of detect this? How do we handle this? That is one question. So, we need some theoretical tools for characterizing the issue first, and then detecting and then removing that issue. So, in this process we will introduce what are called normal forms. So, there are various kinds of normal forms, they are written like this: first normal form, second normal form, third normal form, and a stricter version of third normal form called Boyce-Codd normal form, etc. So, the first normal form is actually included in the definition of a relation. What it actually says, the first normal form, is that the value stored in a column row in a single cell of the relation, a single cell of the table, has to be an atomic value. This we have seen as the fundamental property of the relational model itself. In the relational model, we said that it is a relation is a set of tuples, and a tuple has components, and each component is exactly one atomic value. We do not allow sets, lists or anything like that in that component. This is the fundamental property of relational database. So, the first normal form basically says, restates that, and it is kind of included in the definition of a relation. And the other normal forms, like the second normal form, third normal form, Boyce-Codd normal form, these are all defined in terms of a notion called functional dependencies. So, this is a important central kind of concept for discussing normal forms and the various kind of problems that arise due to bad schemes. So, a notion called functional dependencies is used, and then we will define this normal form. So, we will spend considerable amount of time in this module to kind of understand this central important issue of functional dependencies, and then how do we handle a bunch of functional dependencies and etc. So, immediately after this slide we will start looking at functional dependencies. Then there are these other normal forms. Okay. So, as the normal forms are actually listed in their strictness, in the order of their strictness. So, the second normal form is less strict compared to third normal form. Third normal form is stricter than second normal form. Boyce-Codd normal form is even stricter than third normal form. What do we mean by stricter is that, as I told you, that these normal forms are basically certain kind of conditions. So, if these conditions conditions to be satisfied by the schemes, database schemes. So, when you lay down, if you say that this particular this is the BCNF can be thought of as a set of all database schemes that satisfy these conditions, is the class called BCNF, and that class is smaller than the class of 3NF. That is a set of all database schemes that satisfy certain other conditions. Okay. So, we will see them see these details as we go along. So, that is why we call this Boyce-Codd normal form as a stricter normal form compared to third normal form, and fourth normal form is a stricter normal form compared to Boyce-Codd normal form, and then finally, what we have what is called fifth normal form or project joint normal form, which is defined using. So, the fourth normal form is defined using what are called multi-valued dependencies, which are a generalization of functional dependencies, and then project fifth normal form is actually defined using what are called joint dependencies. Okay. So, we will start looking at these this notion of dependencies. We will start off with functional dependencies, and actually we will spend a lot of time on functional dependencies, a little less time on multi-value dependencies, and almost we will just give a introduction to project joint normal forms using joint dependencies. Okay. So, let us start with this notion of functional dependencies is a very central notion for this theory of dependencies, and it is not very difficult to understand this, actually it is pretty easy. So, a functional dependency FD, it is called FD functional dependency, and it has a left hand side and right hand side and an arrow. So, do not read this as implies, it is to be read as determines, x determines y, x determines y, functional dependency x determines y, where x is actually a subset of attributes of R, y is also a subset of attributes of R is the scheme, R is the relation scheme that we have. So, on the relation scheme R, if you take two subsets x and y, then we say that a functional dependency x determines y is said to hold on this particular scheme. Now, the definition is that if any instance R on the scheme capital R, if you take two tuples T1 T2 which are not equal to each other, T1 T2, and if those tuples agree on the x values, that means the corresponding values are same in both tuples for all of these attributes in x. Okay. You can also write it like this, T1 x equals T2 x, where what is T1 x? T1 x is the subtuple of T1 consisting of the values of attributes in x. Okay. X is some bunch of attributes. So, you take the subtuple corresponding to these attributes, and then of T1 you will get some tuple, right. So, if T1 x is same as T2 x, then it should be the case that on y also these two tuples agree, T1 and T2 agree on y also. So, to kind of summarize this, what x functional dependency x determines y is said to hold on scheme R if T1 x equal to T2 x implies, logically implies T1 x equals T2 y, that is all. If they agree on x attributes, they should agree on y attributes. We will give examples of this. Okay. So, here is one interesting note. Suppose K, some set of attributes of R is a key for the relation R, then you will notice that the key functionally determines or determines A for any attribute of the scheme R. Okay. So, if you now see apply this definition and then see this, I will pause here for you to understand this particular thing. You try to apply this definition for this, K determines A, where K is some key actually. Okay. K determines A. You will notice this to be true. Why is it true? On any instance, on any instance of data on the scheme R, what we are saying here is that if two tuples agree, on values of k, then they will agree on values of A. But then the property of k is that it is a key, right, it is a key. So, can two tuples in the data instance ever agree on k? Can two tuples have exactly same values for the attributes in k? Right? They cannot have, because it is a key. No two tuples in the instance can have same values for the attributes of k. And so, if you see this condition saying that if two tuples agree on x, then they should agree on y. So, if you read that as an implication, then that implication is actually vacuously true in this case. The implication is vacuously true, because there are no two tuples that agree on the attributes of the relation, attributes of the key, right. So, because of the definition of key, there are no two tuples in the data instance that agree on attributes of k. And so, this implication always holds good, because the antecedent of this implication, which says that if two tuples agree on x attributes, then they should agree, the antecedent says that they should agree on x, and that antecedent never holds, it is always false, and so the implication is always true. And so, you can see that if k is a key, k determines A for any attribute A. So, this gives you a simple example of a functional dependency straight away. If you know the key, then key determines A and then actually any attribute of the thing. So, it fits the definition. Are there any questions here in understanding this definition of the functional dependency? I will give you more examples and we will see if you have any questions. Let's take this. Let's take a slightly different scheme here. I am actually in this module, be careful that I am changing the schemas as per the need of the illustrations that I have to give, and so there are different in different slides. So, student, let us look at this particular scheme, which says student name, roll number, which is a key, sex, the gender of the student, department, the department to which the student belongs to, and then hostel name. Let us assume that the students reside in a residential campus. So, they have hostels and each hostel has a name, hostel name, and let us assume that room numbers, rooms in the hostel are all numbered from 001 to some whatever number that is needed. So, it is just numeral numbers, some actually you can think of it as a string also. Room number is a just a number. In particular, I am emphasizing this because it is possible for you to make these room number values in such a way that it can actually also has some numeric some characters inside that which will indicate what is the hostel and things like that. Let us assume that such a thing is not done. Okay. So, the domain of room number, you can make it a string and then put some characters which will indicate as to what is the hostel in which that room is there, and in which case then the room number kind of becomes unique, right. It can uniquely identify any room in any hostel of the campus. So, let us assume that such a thing is not done, just for illustration purpose. So, room numbers are simple numbers, okay. Room numbers are numbers, then hostel name. So, Now, you can see in this setting, let us try and identify some functional dependencies. So, obviously, since roll number is a key, roll number determines everything else. So, roll number determines student, roll number determines sex, roll number determines department, etc. So, roll number, now the way we write these functional dependencies, we should write them in such a way that the left hand side is a set, right hand side is also a set, okay, set of attributes. Now, if for some reason the attribute is alone, then we take the liberty of not putting the set, we simply write it like that. Okay. So, now roll number determines all these attributes. This is obviously true, because in any instance of this particular relation, there will not be any two tuples which agree on roll number, and so they do not have to. The definition of functional dependencies, the implication that is mentioned in the functional dependencies is vacuously true, and so such a situation of two tuples having same roll number will not occur. Or even if in case by mistake some a data tuple comes inserted into the instance with the same roll number with some different this ones, then you can actually the system will catch that, because you also stated that roll number is a key, and so such a issue does not arise. Anyway, good. So, this is one some kind of a easy functional dependency that we can identify here. Now, let us make an assumption here that each student is given a hostel room exclusively. Okay. So, everybody is given a room exclusively. So, no two people are going to be put in a room. Now, if this assumption holds good, sometimes it holds good, probably not always. Okay. So, let us assume that in our institute, that in a certain university, that assumption holds good, or in the domain our assumption holds good. So, if each student is given a hostel room exclusively, then the hostel name, room number together determine roll number, right. So, if again what you will see here is that since there are no two students that are going to have same hostel name and room number, in fact, hostel name, room number becomes a key for this particular thing, becomes a key. You understand that, right? Since we are making this assumption that each student is given a hostel room exclusively, hostel name, room number can together identify a unique student, and so hostel name, room number together actually becomes a key, and since again it is a key, so hostel name, room number determines any attribute, in particular roll number. So, again this example also is following from the principle that the key determines all other attributes. So, this became a key, but okay. Now, let us look at even a little different kind of an example. Let us make this assumption that boys and girls are accommodated in separate hostels, which is usually the case, right. So, let us assume that boys and girls are accommodated in different hostels. Then you can see that now hostel name determines sex. Hostel name is by itself not a key. See, hostel name is not a key, right. There are hundreds of people who are staying in the same hostel, but now you tell me the hostel name, I will tell you whether the student is a boy or a girl, right. That is what I am saying here. So, again this comes from the assumption that the boys and girls are accommodated in separate hostels. So, in the domain it is the case like this, and so hostel name determines sex. That means, if there are two rows in this particular relation which have the same hostel name, say Krishna or something like that, then you will find that those two people are boys, assuming that Krishna hostel is reserved for boys. Then now we have multiple hostels for girls, right? I think there used to be a case where there is only one hostel for girls in our campus a long time back. Anyway, so those names of hostels which accommodate girls, for example. So the moment you give any, so if a row, if two rows have two values, like Sarayu, I think is one of the hostels for girls, right. So then you can then you can't find those two tuples having different sex values. One cannot be male, one cannot be female. Now the other way around is the other way around true? Does sex determine hostel? This is obviously not true. Why? Given that some person is a boy, there are multiple hostels in which the boy could be staying. So you cannot determine what hostel this student is staying. Same is the case. It used to be the case that we have only one hostel for girls, but now I think that assumption is also not true, right. So given sex value, gender value, you cannot determine the hostel name, because there are multiple students, I mean multiple hostels in which boys are accommodated, again multiple hostels in which girls are accommodated. So now you see that this is an example of a functional dependency that holds between two attributes of a relation. So this is kind of giving you some additional information about this student, which is actually domain dependent. I mean, it is in this domain, in this while modeling this, we will be able to figure out that certain assumptions hold good in this model, and so certain functional dependencies hold good on the relation. Okay. So this actually brings us to the question as to who gives these functional dependencies. How do we find these functional dependencies? Okay. So these functional dependencies have to be have to be given or have to be figured out by the designers of the scheme, who are studying the domain and then finding out what are the assumptions that are valid in the domain, what assumptions are not valid in the domain, what knowledge in the domain. So based on that, we will have to come up with these functional dependencies. Okay. So you cannot, just like a key can never be determined by just looking at the instance of a relation, right. By looking at the instance data that is there in the relation, you cannot determine what is a key, right. So in a similar way here, by just looking at data, you may not be able to for sure determine what are functional dependencies. Of course, you may do some analysis and then figure out, saying that most of the data seems to be giving rise to this kind of a thing. I mean, is this really true in the domain? You may pose it to the designers saying that, but it is ultimately the designers who understand the domain have to decide as to what are these functional dependencies that hold between the okay. So now let me so I encourage you to in your schema design that you are coming up, examine the assumptions that you have made, or what are the appropriate assumptions for your domain, what is the domain knowledge, and based on that try and figure out what are the functional dependencies that hold between attributes in your scheme and then make a note of them. Now, a few things that we have to some corner cases we have to fix is that if a functional dependency x determines y is there, then there are other various cases that might arise. What if y is a subset of x itself? Is that a functional dependency? Well, it is a functional dependency, but it always holds good. If y is a subset of x, if the right hand side is a subset of x, then if two tuples agree on x, they will always obviously agree on y also, because y is a subset of x. So, it always holds good. So that is such a kind of a dependency is what is called a trivial functional dependency, because it always holds good in all schemes, in all data. Okay. Now, if y is not a subset of x, then we will call such a functional dependency as a non-trivial functional dependency. So, whether it holds or not, it depends on the underlying domain. So, it is a non-trivial functional. So, what this says allows you is to have, if y is not a subset of x, y might have some attributes in common with x. Y and x may have some common attributes, okay, in this case. So, if y and x do not have any common attributes at all, then we call that as a completely non-trivial functional dependency, and these non-trivial functional dependencies, whether they hold or not, depends on the domain actually. So, maybe we will stop here for today, and I will give you further examples of functional dependencies and how functional dependencies are going to be used in defining the normal forms in the next lecture.